I'm back.
Hello everyone, and welcome to episode 16 of About Our World. And no, your favorite YouTube channel didn't fall off the face of the planet. In fact, I actually finished the script for this video 3 months ago, so... procrastination, am I right? First of all, what is a fossil?
That's just a stupid boulder!
It's not just a boulder! It's a rock!
But we'll continue on that later. The word fossil comes from the ancient Latin word fossis, which means dug up. A fossil is defined by Britannica as a remnant, impression, or trace of an animal or plant of a past geologic age that has been preserved in Earth's crust. Many sources share slight variations of that definition. Fossils can come in the form of bones, imprints, amber, and even feces. There are roughly 4 agreed-upon types of fossils: body fossils, mold fossils, permineralized and petrified fossils, and trace fossils. Body fossils are the picturesque fossils, those being bone fossils. They also include things like frozen animals, petrified wood, and amber fossils. When a small plant or animal gets stuck in tree sap, that sap can harden and form amber. In this amber, soft tissue is preserved for tens of millions of years. This is extremely useful for studying ancient invertebrates and flora. This type of fossil is also how they got dinosaur DNA from the fossilized mosquitoes in Jurassic Park. Basically, any process that preserves the body of an organism in 3 dimensions is a body fossil. The second type of fossil is the mold fossil. Mold fossils are exactly what they sound like: fossils that form a mold or imprint in the ground. These can be shell imprints, scale imprints, or even entire body imprints, as is the case of the blue lake rhino in Washington state. Permineralized and petrified fossils are fossils that are preserved essentially in 2D. Like with most fossils, rock replaces the organic material so the shape of the ancient organism is preserved. The last fossil type is trace fossils. Trace fossils are just any fossil that display any traces of life without any organisms being present. Some examples are footprints, tracks, trails, nests, burrows, even fossilized species called coprolites, and best of all,
Eggs.
most fossils form when water slowly erodes the organic material of an organism, bone for example, and sediment replaces it. That's right, fossils are just rocks, not bones. If Darwin hadn't come across the bones of an ancient armadillo called a glyptodon, we might have one less line of evidence for evolution. However, fossils are rarer than you may think. Looking at our discoveries, it seems reasonable to assume that fossils are everywhere. But a pattern you'll likely notice is that a lot of fossils come from the same places. For instance, a lot of North American Cretaceous fossils come from Midwestern states and territories like Montana, the Dakotas, and Alberta. This is because almost all fossil types require the presence of water to form. For North America during the Mid-Cretaceous, this water source was the West Interior Seaway, which split it into Appalachia and Laramidia. The inland sea created many geological formations like the Hell Creek Formation in Montana. Popular fossil hotspots include Mongolia's Gobi Desert, the Inland Sea, and the Burgess Shale in British Columbia, Canada. The conditions for fossilization are extremely specific, so the formation of a fossil has very low odds. According to a BBC article, less than 1,000th of all species that ever lived became fossils. First, an animal would have to die in or near a body of water. Next, it would have to be quickly covered in sediment, something like a landslide. Finally, over the next few thousand years, the animal's body would have to be slowly eroded away and replaced with sediment. Even if you get past this tedious procedure, there still isn't a guarantee that the fossil won't just be unidentifiable fragments. The chances of finding a good condition, identifiable fossil are very low, which is why almost all of the fossils you'll see at a museum are casts or replicas of the original. For example, this Dimetrodon from the Harvard Museum of Natural History is a cast, but this Deinonychus is the real deal. You might now be wondering how we know how old certain fossils are. I mean, after a while, all fossils look pretty much the same, right? The answer is through radiometric dating. All living things absorb carbon throughout their lives. After all, carbon is the third most common element in the universe. After that organism dies and is fossilized, the carbon becomes unstable and degrades. The reason why it's called radiocarbon dating is because a specific carbon isotope is radioactive. Put simply, an isotope is an atom of any given element that has a different number of neutrons compared to protons. In the case of radiocarbon dating, the isotope in question is carbon-14. The number represents the atomic mass of the atom, where protons and neutrons are one atomic mass unit. Carbon-14 has the usual 6 protons, but has 8 neutrons, making its mass 14. It's radioactive and therefore degrades into a different element, that being nitrogen-14. According to the latest calibrations, the half-life of carbon-14 is roughly 5,730 years. This means that in 5,730 years, only one half of a sample of carbon-14 would remain and the other half would have degraded into nitrogen-14. Then, 5,730 years after that, half of the remaining radiocarbon would have degraded, meaning it goes from a 1-to-1 ratio to a 1-to-3 ratio. Then a 1-to-7 ratio, and so on. By using this number and the amount of nitrogen-14 the carbon-14 degraded into, we can find the starting amount of carbon-14 in the organism, and by doing so, find out how old the fossil is. However, not all fossils contain radiocarbon. In fact, radiocarbon dating is only effective until about 50,000 years ago. So how do we know how old the dinosaurs were? Well, radiocarbon isn't the only radioactive isotope found in fossils. It just so happens that uranium-238 is also found in fossils. And no, I didn't say that wrong. Uranium. You know, the same uranium that powers nuclear reactors and bombs. Why is this highly radioactive element found in fossils? I don't know. Okay, I'm editing right now and I searched it up. It's because, I'm quoting here, organic remains, especially debris from prehistoric plants, create chemically reducing conditions in sedimentary rocks. These conditions cause uranium ions carried in groundwater to precipitate in organically enriched zones in the sandstone. And what that basically means is that they create conditions that can create radioactive isotopes. And since uranium ions travel in groundwater, they are absorbed into these organic remains, making them radioactive. Uranium-238 degrades into lead-206. By finding the amount of lead-206 that was formed, we can find the age of especially old fossils. The reason why this works is because unlike radiocarbon, uranium-238 has an extremely long half-life. To be exact, 4.5 billion years? What? That's literally the age of the Earth. If there was like 10 grams of uranium-238 on Earth when it was forming, there would still be 5 grams left today. If there was a sample of 10 grams at the beginning of the universe, 3.1 grams would be left today. What? That's insane. And that's in fossils. It's just, I don't even know anymore. Like radiocarbon and uranium, there are many methods of using radioactive isotopes to find the age of fossils, or really any rock. Some of these isotopes are aluminum-26, chlorine-36, argon-39, cobalt-60, and cesium-137. Additionally, thanks to the law of superposition, we know that rocks found deeper underground are older. So we can say that certain organisms live before or after each other based on where they are found relative to each other. There are so many fossils we haven't yet discovered, many more we may never discover, and countless species that are completely lost to time. So let's do as much as we can with the ones we've got. I'll see you later.